Okay, let's unpack this. If you need to ace your next certification, nail that technical section of a policy memo, or, just win an argument about legacy naval systems, this deep dive is for you. Welcome back to the deep dive.
Today, we are undertaking what I'd call a truly surgical mission. We're moving beyond the basics of electromagnetic data transfer and really specializing.
Right.
We need to master the foundational principles of three very specific electromechanical components. These are devices often called the second cousins of the standard synchro.
I love that second cousin framing. It really implies they share some DNA, but they were adapted for completely different jobs.
That's it.
Our core job today is to provide you with the structure, the definitions, and critically, the numbers and the cause and effect relationships that make these components tick. We are going straight into the engineering manual to pull out the most vital nuggets for immediate application.
And we are covering three core categories. You'll find them mostly in shipboard and aircraft applications where you need remote indication or even computation.
Okay, so what are the three?
The IC synchronous, the step transmission systems, and finally the resolvers. You can think of them as three different solutions to the same fundamental problem. How do you reliably and accurately transmit angular data across a distance?
Okay, so to put this into context for everyone, you can think of remote data transfer in maybe three basic ways, based on the engineering trade-offs that were made. Imagine you need to send an angle, a position from point A to point B.
Right, so standard synchros, which operate on AC power, they're kind of our baseline. But today, we are looking at the specialists.
The specialist.
The IC synchro is, let's say, the high torque specialist. It prioritizes brute rotational force above all else.
Okay.
The step transmission system is the DC specialist. It prioritizes simplicity and ruggedness in places where AC just isn't available.
And the third one?
And the resolver, that's the mathematical specialist. Its entire job is to prioritize real-time, continuous calculation.
So we are not looking at generic position indicators here. We're looking at highly customized electromagnetic tools, each one designed to overcome a really specific constraint.
Precisely. All three are fundamentally electromagnetic devices.
Yeah.
But it's their internal structure, the arrangement of their coils, their power source, that dictates their specialized function, whether that function is increased torque, DC operation, or trigonometric calculation.
That sets the foundation perfectly. Let's start with the one that feels the most familiar, but is built in, a truly counterintuitive way. The Interior Communications Synchro. So the name, Interior Communications Synchros, or IC synchros, it pretty much gives away the primary context. These are used heavily on naval vessels. They handle really crucial tasks. We're talking about the engine order telegraph, the steering telegraph, rudder angle indicators. These aren't just displays.
No, not at all. These systems don't just need to display a position. They often need enough rotational force, enough torque, to physically move heavy dials and gear linkages, and to do it instantly.
Functionally, how do they work? Are they similar to what we already know?
Oh, yeah. Functionally, they rely on the same interacting magnetic fields as a standard synchro to transfer that angular data. But for someone prepping for an exam, you really need to lock in the two key outcomes that make IC synchros unique.
And those are?
The specific way the shaft rotation operates and, this is the big one, the vastly increased amount of torque they can generate.
The source material we looked at notes that while they're still in operation, they are being sort of phased out.
Right, in favor of standardized equipment, usually when the older units fail. But understanding them is still vital for anyone maintaining legacy systems or just trying to understand the evolution of ship controls.
This brings us to what feels like the core concept. They're sometimes called reversed synchros.
That is the key jargon alert. And that one word, reversed, it dictates everything else about their operation. The reversal describes where the primary excitation winding, the coil that receives the input power, is actually located.
Okay, let's define that structural reversal clearly, because this is the fundamental distinction from a standard synchro, and it sounds like a critical cause and effect relationship.
It is. In a standard synchro, the primary winding, the one that gets the excitation voltage, is typically fixed on the stator. That's the stationary outer shell.
And the secondary, the output windings, are on the rotor.
Correct. But with the IC synchro, it's flipped.
Flipped how?
With the IC synchro, the key structural difference is that the stator, the fixed part, mounts the secondary winding. This secondary is made of two coils connected in series.
Okay, so the output is on the fixed part, which means?
Which means the rotor, the rotating element, mounts the primary winding. This primary consists of 3 coils connected in what we call a Y configuration.
So that's the reversal.
That is the defining feature. Primary power on the spinning rotor, secondary output on the fixed stator.
Wait, if the primary power is being applied to the rotor, the part that is physically spinning, how does that power get there continuously? That immediately sounds like a mechanical headache.
That's a key observation. You're exactly right. Since the primary winding is rotating, the AC excitation voltage has to be supplied through slip rings and brushes.
Ah, so there's a physical contact point.
A major trade-off. While those mechanical components, the slip rings, allow for the electrical reversal you need to get that high torque, they also introduce wear, friction, and a pathway for mechanical failure and electrical noise. It's nothing like a standard synchro where the fixed stator is just excited directly.
Okay, that really clarifies the mechanical challenge that's introduced by that electrical design choice. Let's just do a quick recap of that reversal nugget for the listener.
That idea.
IC synchros transfer information using standard synchro principles, but their structural key is the reversed placement. The primary, that's the excitation with 3 Y-connected coils, is on the spinning rotor. And the secondary, the output, with 2 series-connected coils, is on the fixed stator.
And that Y-connected primary winding, by the way, is essential. It's what allows it to generate a strong, stable, rotating magnetic field when you apply AC power to those 3 distinct phases. It's a very standard configuration for efficient power distribution.
Okay, so now let's move to the operational consequence of this reversal, which is the directional effects. This has got to be critical for system integration.
Absolutely. The standard operational goal is always synchronization. In typical setups, which you'll see called View AB in the technical manuals, when an IC transmitter and a matching IC receiver are connected in parallel, the IC receiver shaft just follows the rotation of the IC transmitter shaft.
They move together.
They operate in sync.
But the design also allows for, or sometimes even mandates, opposite rotation.
Precisely. And this is the reversal effect you have to track. When your system constraints make it desirable to have the IC synchro receiver turn in an opposite direction from the transmitter.
Like, say, if the indicator needs to move clockwise when the remote source is moving counterclockwise?
Exactly that. In that case, the specific connections must be changed. Engineers have to deliberately cross the winding leads to compensate for the inherent electromagnetic phase shift that's caused by the reversal. This is often designated as view C in the diagrams.
So the cause, that internal winding reversal, is what makes the rotational effect so sensitive to how you wire it up. What happens if you, I don't know, try to mix component types, like an IC transmitter with a standard receiver?
That provides the clearest proof of the reversal. If you connect a standard synchro receiver 1 that's designed for a primary winding on its stator to an IC transmitter, the result is an opposite rotation by default.
Oh, automatically.
Automatically. You'll see it as view D in the manuals. This rotational difference is an inherent electromagnetic characteristic that comes from the IC winding configuration. It forces system designers to always anticipate and compensate for this directional difference, either in the hardware or in the wiring.
Okay, to summarize that directional consequence for everyone studying, mixing an IC transmitter with a standard receiver defaults to opposite rotation. To get a desired opposite rotation within an all-IC system, you have to physically swap or cross the connections. It's all about managing the phase relationships.
Perfect. Now let's move on to the whole reason for the IC synchro's existence. The massive torque advantage.
This is where it gets really interesting for me. If the goal is just remote transmission of angular data, why not just use a standard synchro and maybe some mechanical amplification? Why build this reversed slip ring reliant device?
Because the torque you can achieve is intrinsically tied to the magnetizing power the device can handle.
Okay.
And the magnetizing power itself is constrained by how much heat the machine can dissipate without, well, melting.
Right, without overheating.
In an IC synchro, since that massive stator housing is holding the secondary, the output winding, we can put the primary winding, the main heat source, on the rotor and then dramatically increase the magnetizing power.
And the effect of that increased power?
It results in a significantly larger torque. This is a crucial cause and effect chain you need to remember. Increased magnetizing power leads directly to increased rotational force, or torque. This brute force is why IC synchros are perfect for systems like engine-order telegraphs that have to physically turn heavy linkages or large, stiff indicator pointers.
But, as you pointed out earlier, increased power means there's a trade-off. Heat. If the primary power source is now on the rotating element, the rotor, that changes the entire thermal signature of the device, which has to be a key operational characteristic.
Absolutely. This is a critical point for maintenance and for design. In a standard synchro, the heat loss is primarily dissipated through the stator housing. It's fixed, it's typically easier to cool, maybe through contact with the mounting base or just ambient airflow.
But in the IC Synchro, that heat source is spinning.
Exactly. In the IC Synchro, the major heat source is the primary winding on the rotor. So the heat loss must first dissipate through the rotor structure itself. Then it has to jump the air gap to get to the stator, and then finally it dissipates through the outer shell to the surrounding air.
And that air gap is an insulator.
A huge insulating barrier. This difference means IC Synchros run hotter, and they require much greater consideration for mounting and for ambient temperature limits to prevent the windings from degrading.
So if I'm hearing you correctly, the entire viability of the IC Synchro really rests on its ability to cool itself effectively, despite the fact that the heat has to cross the mechanical air gap. That seems like a major maintenance liability compared to a standard design.
It is.
It's trading thermal complexity for mechanical robustness.
That's the perfect synthesis of the engineering trade-off.
Hmm.
And just finally, one last numerical definition to lock in for the exam. The electrical zero position for an IC Synchro. It's defined as the position where the rotor coil that's labeled R2 is aligned, both physically and electrically, with the defined stator position. This is the baseline, the reference point for all of its angular measurements.
That wraps up our specialist on AC power and high torque. Now that we've solved the high torque AC problem, what happens when we don't even have AC power to begin with? That's where the step transmission system, well, steps in. This is a completely different design philosophy, isn't it? We are transitioning from high torque AC specialization to simple, rugged DC functionality. We should probably start with the necessity of the step system. Why does it exist?
The necessity is purely environmental and, I'd say, foundational. While AC power is ubiquitous today, historically, many large naval and merchant ships relied entirely on DC direct current generators for their essential operational power supply.
So the core cause is just the absence of an AC supply, and the effect is the requirement for a fundamentally different electromechanical solution that can operate entirely on DC power.
Precisely. The step transmission system, or sometimes called the step-by-step system, was engineered specifically to transmit angular data in these DC-only environments.
Where would you typically find one?
You'd commonly find it used as a geared system to drive things like magnetic or gyro compass repeaters. It takes the angular information from the master compass and sends it remotely to, say, the bridge wings or the pilot house.
Let's break down the mechanics. It's still a transmitter-receiver pair, I assume, but it sounds like it relies on sequential switching rather than those continuous magnetic fields we saw before.
That's exactly right. The system consists of two parts. First, the step-by-step transmitter, which is essentially just a robust rotary switch. It's driven by the input shaft, like from the master compass.
And the second part?
The step-by-step motor, which is the receiver unit.
So how does that rotary switch translate a position into steps?
As the transmitter shaft rotates, the rotary switch inside makes and breaks a series of electrical contacts sequentially. These contacts periodically supply a DC excitation voltage, often the ship's 28-volt DC bus, to specific coils of the step motor.
And then the motor shaft turns.
It turns, but by a discrete, fixed amount that's proportional to the transmitter shaft's movement.
This brings us to the critical numbers, the ones that define the motor's construction. This sounds like exam territory.
Definitely exam territory. The numbers are exact and they determine its function. The step motor stator has 6 field coils.
These coils.
These coils are spaced precisely 60 degrees apart around the stator housing. They're internally connected in 3 groups, with the opposite coils connected in series, and that's to make sure the magnetic field is stable and strong. This configuration, 6 coils, 60 degrees apart, is the physical key to its entire operation.
And the armature inside, what's that made of?
It's typically just a soft iron armature. It's not a permanent magnet or anything complex. It's simply drawn towards the strongest magnetic field that's generated by the coils at any given moment.
Okay, let's follow the DC current path to really understand the stepping action.
Sure. The DC battery voltage is applied through brushes on the transmitter to sequence the energizing of those 6 coils. This produces a rotating magnetic field, but, and this is the key, not smoothly. It does it in discrete steps.
Can you give an example of the sequence?
Yeah, for instance, the sequence might be step 1, only coil 1 is energized. Step 2, coils 1 and 2 are energized together. Step 3, only coil 2 is energized, and so on. It creates a progression of magnetic vectors around the stator.
This is where that inherent limitation really becomes apparent, isn't it? Because the armature is being pulled kind of abruptly to the next energized magnetic vector. The motor armature has to rotate in abrupt increments or steps.
Right.
It's not the smooth, continuous sweep you'd get from an AC synchro.
Exactly. And this leads to the numerical limitation that you absolutely must memorize. The armature typically rotates in discrete 30-degree steps. While, specific designs might vary, the key takeaway is that the increment is large and abrupt. It's not fractional or smooth at all.
Wait, a 30-degree step size? That sounds almost unusable for any modern high-precision navigation or, say, weapons tracking. If the rudder angle changes by just 5 degrees, the indicator might not even move.
That's right.
So why didn't engineers try to break that down further? I mean, why not use 12 coils or more complex switching?
That's where the trade-off of simplicity comes right back in. While you could absolutely increase the number of coils to decrease the step size, that would drastically increase the complexity of the rotary switch transmitter.
And the cost?
And the cost, and the maintenance burden. This system was designed for reliability and simplicity in a harsh environment. For a basic compass repeater, which moves pretty slowly, and where a 30-degree positional error is, well, acceptable for long-term navigation, the simple 6-coil design was more than sufficient.
That frames the step system perfectly. It's an engineering compromise where simplicity and cost completely override precision. Let's do a quick recap on this DC workhorse.
Sounds good. So recap. Step systems use DC power. They're defined by their reliance on a rotary switch transmitter, exciting 6 stator coils, which are 60 degrees apart, on the receiver motor.
And this causes the soft iron armature to rotate in those discrete 30-degree steps, or sometimes even greater.
Correct.
Now let's discuss the critical operational disadvantages of using this system. These feel vital for understanding the policy shift toward digital or AC systems later on.
The 2 main drawbacks are significant liabilities in any complex system. First, and this is a big one, the system is not self-synchronizing.
What does that mean in practice?
Well, a standard AC synchro automatically aligns itself to the transmitter's position the moment you apply power. That's due to the continuous nature of the AC magnetic field. The soft iron armature in the DC step motor, however, requires an operator, or a dedicated reset control, to manually align the receiver with the transmitter every single time the power supply is energized.
Or restored after an outage. Wow, so that introduces systemic human error and a significant downtime risk, especially in dynamic environments like a ship at sea, where power interruptions are pretty common. You have to physically re-zero the whole system.
Absolutely. The second major disadvantage stems from the structure we just talked about. Limited resolution.
The 30-degree steps?
Because the angular data is transmitted in these abrupt, large steps, 30 degrees minimum, the system simply cannot transmit or register small changes in data smoothly or accurately. This inherently limits its application to systems that do not require high granularity.
So, from a policy standpoint, the step system is inherently flawed for any kind of real-time, high-precision control loop. However, it must still hold some relevance.
Its policy relevance really lies in its robustness. The system is cheap, rugged, and actually relatively powerful for its size. It's incredibly reliable under DC power, and it's simple to maintain. It is the perfect fit for applications where high precision for small fractional changes is just not required.
Like early warning indicator flags or basic backup indicators?
That's it. It's the very definition of good enough for the job.
Okay, so you've covered the high-torque brute force device and the simple, rugged DC device. Now we move to the most complex of the three, the brain of the operation. The device designed not just to transmit position, but to solve continuous mathematical equations. Let's dive into the resolver. A resolver, it might look like a synchro on the outside, but its function is completely different conceptually. It's not just a signal repeater, it's a dedicated mathematical component. What's the fundamental definition we need to start with?
A resolver is a specialized rotary electromechanical device, and it's used to perform mathematical computations electronically. Its core function is to produce voltage outputs that directly correspond to the trigonometric functions of its inputs.
So specifically sine and cosine.
Specifically the sine and cosine of the angle of rotation.
So it turns mechanical rotation into pure, usable trigonometry, but in the form of proportional voltage outputs.
Precisely. Imagine trying to constantly solve thousands of right triangle problems per second by hand. That's what a resolver does instantly and continuously. They are absolutely crucial components in First and second generation analog computers, radar sets, and any sophisticated direction or target designation equipment.
So the ultimate advantage, and really the reason they dominated real-time control before digital microprocessors took over, is that they give instantaneous, continuous solutions as the input quantities change. There is zero delay, as long as the input voltage is changing.
And the architecture explains why this is even possible. The source describes a resolver as being fundamentally similar to a transformer. This is key. It's an electromagnetic component where energy is transferred between primary and secondary windings, all through a magnetic field.
But the twist is that the amount of magnetic coupling is variable.
Correct. The resolver achieves its mathematical function because the secondary windings, which are on the rotor, can be mechanically rotated relative to the primary windings on the stator. This rotation varies the magnetic coupling between the fixed and rotating windings, and that variation in coupling inherently generates the trigonometric function.
Okay, let's get into the structure. This is where the numbers are going to be critical for exam purposes. The physical arrangement has to be what ensures the output is sine and cosine.
The geometry must be exact. The stator contains two windings, and they are placed precisely at 90 degrees, a right angle to each other. Because they are electrically and physically perpendicular, there is zero magnetic coupling between the two stator windings themselves.
So if you energize one, the other one doesn't see anything.
The other receives no induced voltage. They are isolated.
And the rotor mirrors this 90-degree separation.
Yes. The rotor also contains two windings, similarly placed at 90 degrees to each other. And again, within the rotor assembly itself, the windings are isolated from one another. The rotor, of course, is mounted on a shaft that's capable of unlimited rotation. This internal isolation is what ensures that the outputs are always true orthogonal components.
Let's talk about accuracy for a minute. Given that these are analog devices generating continuous math, minute variations must introduce errors.
They absolutely do. The resolver is a high-precision component, far more sensitive than a standard synchro. To increase its accuracy, the technical manuals describe compensator components, things like resistors, capacitors, or even additional windings that are integrated either internally or externally.
And what do they do?
These components compensate for inherent non-idealities, like tiny voltage inaccuracies or phase shifts, ensuring the output voltage truly reflects the pure sine and cosine of the input angle.
So that 90-degree geometry is the functional definition. Let's do a quick recap on resolvers before we look at the specific computations they can do.
Good call. Recap. Resolvers are analog computing devices. They utilize the critical geometry of two right-angle windings on both the stator and the rotor. This configuration generates outputs proportional to the sine and cosine of the angle of rotation, providing continuous, instantaneous mathematical solutions for real-time control systems.
Okay, now let's look at their two primary computational roles, resolution and composition. Let's tackle resolution first.
Resolution, to put it simply, is the process of breaking down a single vector quantity into its two orthogonal components.
So it's X and Y component.
Exactly. Think about calculating how much of a ship's movement is forward on the x-axis versus how much is sideways on the y-axis when it turns at an angle.
So the resolver is fed the known magnitude and the known direction, and it just spits out the X and Y components instantly. How does the device achieve that cause and effect relationship?
It's a three-step process. First, the input magnitude. The known quantity, which is the vector's magnitude, we'll call it E cirrus, is typically an AC voltage. That's fed to just one of the stator coils.
Okay, just one.
Second, the input angle. The angle, we'll call it R, representing the direction, is set mechanically by physically turning the rotor shaft to the desired position.
And then the output just appears.
Third, the output components. As the rotor turns, voltages, let's call them E$ and E2$, are induced in the two separate rotor coils.
And these output voltages, $E and $2, what are they?
They represent the vertical and horizontal components of that known quantity.
Yeah.
Since the coupling varies trigonometrically, E$ might be proportional to E$ times the cosine of R, and E$2 would be proportional to E$ times the sine of R. The output is dependent simultaneously on both the magnitude dollars and the angle R through which you turn the rotor.
That's powerful. I mean, that's the fundamental tool for taking raw sensor data like a detected radar range and breaking it down into usable coordinates for a targeting computer.
Exactly. It converts polar coordinates into rectangular coordinates in real time. Now let's look at the reverse operation, composition.
So composition is vector addition. We take those two right-angle components, X and Y, and we combine them to produce the single resultant vector. And that gives us the hypotenuse, which is the resultant magnitude, and the direction, the resultant angle.
Here's the reverse cause and effect process. First, the input components. Two known right-angle components, $1 and $2, are fed to the two separate stator coils. For example, the horizontal speed and the vertical speed of something.
Okay.
Second, the output, magnitude. A voltage, let's call it $1 proportional to the magnitude of the hypotenuse, the true speed, or the resultant vector, is induced in one of the rotor coils.
Okay, that solves the magnitude problem. But how does it find the resulting angle? Does the operator have to turn the shaft manually until the answer just appears?
Not in a modern system, no. This is where the closed-loop control comes in. The voltage induced in the other rotor coil is designed to be fed directly to a closed-loop servo system.
A servo motor.
Right. This servo motor constantly measures the voltage on that second coil, and it drives the rotor shaft until that induced voltage is driven precisely to zero.
So the resolver is constantly adjusting itself mechanically until it hits a null point,
Yeah.
a 0 point.
Yes. When the voltage on that second coil is zero, it means the rotor shaft is now mechanically positioned exactly at the resultant direction, the angle of the hypotenuse. The system is actively, physically finding the solution in real time.
That is absolutely critical. The resolver doesn't just passively give you the magnitude. The second output voltage actively drives a control system to find the correct angular position. It makes it a truly self-solving component.
And finally, the sources we reviewed also mentioned that resolvers can perform a third function called combination. This is basically the simultaneous process of resolution and composition happening within the same system. This complexity is what allowed sophisticated naval systems to solve complex geometry problems involving multiple distances, speeds, and angular quantities all at the same time, in real time.
Wow. Okay, given the extreme mathematical precision that's demanded by resolution and composition, let's just reiterate the operational warning.
The precision warning is absolute. The resolver is a system of, let's say, zero tolerances. Any deviation in the electrical characteristics, winding resistance, phase shift, harmonic distortion, or any physical wear will cause that output trigonometric voltage to be incorrect.
And that introduces errors into the whole loop.
Excessive errors. Maintaining this precision requires dedicated, careful calibration and constant reference to the technical manual for the exact specifications of that one particular component.
Okay, we've covered 3 very distinct engineering responses to remote data transfer challenges. Let's try to synthesize these devices now based on our core trade-offs.
Yeah, if we connect this all to the bigger picture, you should now see these 3 devices not just as components, but as artifacts of an engineering philosophy, a philosophy that's driven by constraints, whether that's needing high torque, needing DC power, or needing instant calculation.
Let's break down that synthesis by constraint one last time, really focusing on the exam differentiators.
Okay, IC synchros are the AC torque specialists. Key features to remember: reverse primary on the rotor and secondary on the stator windings. The trade-off is increased magnetizing power, which results in high torque, but it requires dissipating heat across that critical air gap and relying on slip rings for excitation power.
Next up, step systems. These are the DC necessity key features. 6 coils spaced 60 degrees apart, excited by a rotary switch. The trade-off here is robustness, simplicity, and low cost, but critically limited by low resolution, those degree steps, and the operational requirement for manual synchronization after any power cycle.
And finally, resolvers. These are the AC computational experts. The key feature: 2 windings on the stator and 2 on the rotor, all of them orthogonal or 90 degrees, to their internal partners. The trade-off is extremely high precision and a continuous instantaneous mathematical output sine and cosine, but it relies on perfect component alignment and electrical characteristics.
Okay, we absolutely need to nail the power source and output differentiation for clarity.
Right. Power source. Synchros and resolvers use AC. Step systems use DC.
And the output.
The output is the big one. Standard synchros and IC synchros provide angular position. Step systems provide angular position, but in large, discrete steps. Resolvers provide trigonometric voltage outputs. The voltage is proportional to the sine or the cosine of the angle. The fundamental problem solved by the resolver is the right triangle or trigonometric problem.
So these analog components were the basis of really complex command and control systems like plotting aircraft trajectories or directing artillery, long before digital microprocessors could handle the volume and speed of required calculations robustly, especially in harsh environments.
They gave engineers real-time control.
And as we shift towards modern systems, it's worth considering the long-term cost of that analog precision. We talked about the resolver's reliance on mechanical contact, those rotor slip rings, to transmit continuous trigonometric voltages.
That mechanical interface, which is required for continuous rotation and signal transfer, is really the Achilles heel of any analog control system. It's subject to contamination, wear, and variable contact resistance, all of which directly affect the output voltage.
So here is the provocative thought for you to mull over, especially if you're drafting a policy memo on modernization. The resolver gives us the perfect trigonometric answer, and it does it instantaneously, but only if every single mechanical and electrical component remains perfect and unworn. How often do policymakers forget that the complexity of analog precision, which is dependent on mechanical perfection, eventually yields to the inherent reliability of digital approximation?
Hmm.
It forces us to ask, is it better to have a mathematically perfect answer that degrades over time, or a consistently accurate digital approximation that does not depend on moving parts? That question speaks directly to the justification of replacing these fantastic yet fragile legacy components.